Hey everybody, this is Larry. This is day 5 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's poem. Today here in New York City, or this evening here in New York City, it is absolutely pouring. But you know, a man's got to do what a man's got to do, and I did my 10-mile run, 8 mile of it at my hopeful marathon pace, and you saw it in the intro. I don't know what I'm thinking. I think at a certain point, I don't know. But hopefully, it's a little bit motivating for you. If I can do it in the dark, probably start a little bit later than I should. In the pouring rain, soaked to the bone for 2 hours or whatever it was. I think it was 2 hours. 2 hours would be too long. Like an hour and a half. Soaked to the bone everywhere, carrying extra pounds because of the water. You can do this Leetcode poem. So let's go. Let's get started. Yeah. So I could go to bed afterwards. Actually, I should eat something. Yeah. I mean, I did some protein shakes, but I want to eat a little bit more. Anyway, okay. Not that you need a particular life story, but at least not that one. Anyway, let's take a look at today's poem. We have 2749. Minimum operations to make the integer 0. You're given two numbers. In one operation, you can choose an integer I in the range 0 to 60 and subtract 2 to the I plus num2 from num1. Maybe I have to pause that. I mean, we read the words, but what does it mean? Not sure. Return the integer denoting the minimum number of operations needed to make num1 equal to 0. If it's impossible to make num1 equal to 0, return -1. Okay, so you have this number. What does that mean? So, okay. So, oh, I see. So basically, nums2, you subtract this number, right? Okay, I see. I mean, I think the key thing to know is just to figure out what the domain is, right? Oh, right. Oh, maybe I misunderstood this one, actually. Hang on. In one operation, you could do this. Okay, so no. I for some reason, I thought you can only do one operation. This is minimum number of operations. Okay, so hang on. Okay. So I think okay. I mean, now I have to recalibrate a little bit because initially I was going to say a couple of things of like, oh, you just do a loop from 0 to 60. But I think I just misread that, to be frank, right? Obviously. Because, I don't know. I mean, Leetcode has some easy problems, right? So you have to forgive me for doing it. I guess the first thing I'm trying to do is try to figure out, is there like an easy way to figure out the impossible route? Or not, right? So okay, and maybe for me to start with, I would play with some numbers. Let's say nums2 is 0, or I think there are a couple of ways you can explore this, right? Like one is just play around with small numbers. The other is maybe they're trying to fool you a little bit, and you're trying to do the reverse, and maybe and that could be true, but we have to but that could be in some order, right? But okay, let's say nums is 0. What does that mean? Well, that means that this is just a power of 2, right? So okay. So, well, okay. Then that makes... Okay, now actually just saying that out loud, honestly, flicked a light bulb in me, right? What I mean by that is that then it just reduced to... And, and maybe I have to figure out, right? But... that means that, let's say we're able to do one operation. I mean, this is, but when, let's say nums2 is 0, then what does that mean? Actually, skip the one operation part. That means that, well, the answer is just the number of 1 bits, right? Like, num1's binary number, the number of 1 bits, that's the answer, right? For nums2, right? Hopefully, I don't have to explain that one. If you don't understand, and maybe I'm going a little bit fast, just pause the video and see if we can work that out. This should not, I mean, it only gets harder from here. So you have to do a little work to carry this, right? Okay. But then now, after that, okay, so then now maybe nums2 is equal to x, right? nums2, yeah. Right? Then, and let's say we have k operation. Well, then what happens? Well, in k operation, then now we are subtracting some sum of 2 to the I for some, for k of them, plus x times k, right? and then you subtract this. So I mean, it depends how you want to write it. You could say positive or negative, right? So that means that if so that is enough, right? Because then now we can just brute force k maybe. Well, yeah, we could brute force k because the way that I would phrase it is that, okay, let's say you subtract, let's say we have operation or one operation, right? Operation is equal to 1. What does that mean? That means that you have one sum 2 to the I, right? So one of these, which is to say the number of 1 bits is 1, right? And then, but that you also have to subtract whatever the x is times k, but in this case k is 1, right? So that means that if you have num1 minus num2 times 1 in parentheses, if this number has 1 bit, then we're done, right? And then now you try for, well, 2, right? If this number has 2 bits, then, or 2 1 bits, sorry, 2 1 bit. I think I'm saying that a little bit awkwardly, but you know, but you get the idea, hopefully, right? And then now, then your question may be like, well, how do you do the impossible case? Well, the impossible case. Well, in this case, you could say maybe 60, maybe 10 to the 9 is going to be 30, at most 31s. Maybe it's, you know, even double it to 60, or 64, whatever for a long. Just to be sure if you want to play with that, or 60 or whatever, that's also fine. But because then it is just going to be num sub 1 minus num 2 times 60. If this number has, remember, this is exactly, right? If this has 61 bit, then we're done. But keeping in mind that obviously at a certain point, if you dot it out, you can't, you know, as we said, this is num2 times k, and hopefully this pattern is obvious now. If this number has k 1 bit, then we're done. But if and it depends on the domain, which if this is 10 to the 9 or up to 10 to the 9, so maybe let's say this is the biggest number 10 to the 9, and for whatever reason this is negative 10 to the 9 times k, which is not going to be 10 to the 9. We said that it's going to be at most 60, just because, like, you could even say 100, right? Then this is 10 to the 12. Then this is going to be 10 to the 12, and that 10 to the 12 has what, 40 bits, right? So that's in this case, you know. And then you can, if you want to be more exact, you could binary search, but that's not even important, right? We're just setting an upper bound. So like you could say this is 60, you could say 100, but you're fine, because then now you are done. So that would be the upper bound. You try for 100 numbers or 60 numbers or whatever it is, you know, and I would maybe go for 100 just because, you know, it's at least in Python, because you don't have overflows, but also, but yeah, I mean, 100 operations, a loop of 100, these are cheap operations. Checking the number of bits is a cheap operation, right, relatively. So I'm not going to worry about that. And then, yeah, and then after that, if it's not possible, then you just return -1, and that's it, right? So here we can do I'll just use k, because that's what I've been using in my explanation, right? So 0 to say 60, right? And you can maybe put this in a constant, but I'll just leave it here for now. Right, so if, let's just say now is equal to num1 minus num2 times k, right? Yeah, if now that bit count, I think, I always forget what it is in it's either this or like underscore, I always forget, so we'll see. Then we can return k. Can this be 0? I guess if they're both 0, I guess it, then you don't need any operation. Yeah, it should be okay. And then else return -1, right? And that should be good, hopefully. Yeah, I did mean bit count. Thanks, Python thingy. Oh, why did I put -1? Or how did, dong. Oh, this can be a negative number. What happened? So, okay. So I'm a little bit imprecise. But because you're subtracting, huh? That's a little bit awkward. Did I do something wrong? Trying to think. I mean, I'm actually a little bit surprised, not gonna lie. There's definitely a 1. Why? 157 is gonna be -2. I guess I just don't handle negative numbers well. Huh. I actually don't. I mean, I just didn't think about negative numbers. And I don't think. I mean, I'm just thinking that I don't think negative numbers are possible because you cannot subtract any powers of 2 to get back to 0, right? So I have to do something like this. Let's see if that fixes it. Okay, that fixed this one, which is good. But this one, still -1 is no Gucci. Huh. Well, that's okay. I mean, we could. I'm a little bit surprised, but yeah. But we can debug it. 0, 1, 2. I mean, it is correct that this is incorrect, but did I miss a thing? Oh, I am wrong. Because you could choose the same bit twice. Okay, so I'm wrong. Okay. I mean, it's even in the explanation, so it's my fault. But I think the idea is right. We just have to make adjustment to the bit count. And I think the thing that I'm trying to think, I mean, my next generalization is that, well, maybe the exactly E equal to K is true but lazy or not sufficient. But is it if this is less than or equal to K, then I think maybe that's fine as long as this is not 0. Maybe. And the reason is because if you need no, I mean it's maybe, but not actually because I was going to say something like you could combine ones to kind of, but that you still is it like an upper bound, right? I think this is the right idea, but I have to be a little bit more precise. So I was wrong on this for sure. Because this is an upper bound, but that's not sufficient. Like it's necessary, but not sufficient. Wait, is that even necessary? No, it's necessary because if there are more ones than whatever, then it just cannot be true. So okay, right? Because if there are more 1 bits, then you just don't have enough operations to do it, or K is too few operations to do it. Okay, so then now we have to figure out how to do this math, right? For example, this one is true because you can do this 0. You just do that 1 twice, so then you have to carry, right? But my question is whether I can either like I'm trying to think whether I should break this down to do it to kind of calculate it, or yeah, because this one is also true in that sense. Even this one really. Um, hmm. I think I would say like this is like 80 to 90% of the way there, and I'm trying to also, to be honest, if I was in a contest, maybe I would already hack some code together to kind of play around with it, or like YOLO submit it. But I'm trying to think through all the, just be more deliberate, and not make silly mistakes or further silly mistakes, I suppose. I was clearly very wrong on this. So yeah, my excuse is that I just came from a 10-mile run and it's like 2:30 a.m. as a result. So 2:40 now. But like for example, I think here 12 is just that's too many bits, right? You can't even squeeze that in even if you want. Actually, I guess maybe you can. Just keep on giving it once. Maybe. I mean, or at least I could conceive of it. Um, hmm. I have this idea of min bits and max bits. Like k is the max, and then you have a min, which is just the number of bit counts you get from like k, right? Like k dot bit count or something, right? Like something like this maybe. But I don't know that that's right. I mean, even I think this works for this one, but I don't know that that's right for all cases. I'm trying to think. And I guess for that, then we can, I don't know, at least we could play around some test cases, I suppose. I don't know. Though it's likely that those are like -1, so I don't know if that's very helpful or not. Oh, this is actually 2. That's lucky or something. I'm going to YOLO submit, but honestly, I'm not confident about this. Okay. I mean, I guess I should try negative numbers. Why is this not right? Oh, okay. So I just don't do enough. Because I am trying to buy a case, if you will. I mean, obviously it costs nothing now, but if I was in a contest, I might consider buying a case, because trying to come up these cases in a contest, if it costs me 5 minutes, a little bit of a meta strategy to get a wrong answer, but maybe it takes me 5 or more than 5 minutes to come up with this case, then it just becomes more, you know, it's just what you're willing to pay, right? And also you have some chance of getting it YOLO correct. So, but yeah, okay. So the answer is 3. Oh, this is possible? How is that possible? Actually. Now is the, oh, yeah, so K is, wait, what are the numbers again? I don't know why I print this, but not the, it's not very, okay, fine, let's just print it. No, but I mean, I guess this doesn't matter in the sense that now you have 8, you have 3 binary. How does that? Huh? Now I'm not confused per se, but I'm trying to figure out how that is possible, right? Because you have 1. Oh, I see. You could merge 2 of them into 1. I actually did not consider that. Actually, I did. I guess I did, but I didn't. So 3 would be 1 1, but then if you have 1 1 1, and then you go, Now I'm trying to go back and think, like, is it always possible? Maybe it just is. I mean, maybe I mean, I wasn't able to prove it. That's why I didn't want to YOLO it. But maybe it is. Let's see. Okay. That was not the case. Man, today is one of those problems where I'm missing like something clearly. I mean, this is not expect. Because this is 0. Actually, I did. That's why I didn't submit it. This was I mean, not this particular one, but this was the variation that I was like, oh, but if this is 0, then you can. But yeah. Does it have to be just? Does that work? Can you always do it? I guess so, because my logic is that no, it's not. It doesn't work. There's a case where, what is the case I'm thinking of? No, I mean I came up with a case. I don't know. Sometimes when a problem gets too long, I get a little confused because I did come up with a case in my head, but then I just forgot it. It is the case where you just don't have enough bits. But maybe that's not true. Maybe this is fine. Because I was thinking about like, yeah, because you can always just, because the idea was that you can merge 2, but you can actually also merge 3 into 1 bit, so that as a result you can also merge 4 into 1 bit. You just cannot merge to 0, right? So let's try that. Okay. Well, this is because wait, is this not equal to 0? If they're already... Oh, and 1 up. Okay, I messed up. I added this because I just didn't think through it because I am silly. Right. Well, today it's last time I got a lot of wrong answers too, so I guess this is just one of those problems where, listen, we all have our strong points and weak points, and clearly this is a weak point for me, and consistently so. But did I put in? Yeah. Okay. I don't know why oh geez. Okay, so it's not possible to always merge, I suppose. Okay. All right. I'm a little bit angsty about it. At a certain point, I did say, it deliberately you can whatever, but yeah, at maybe 4 or 5 wrong answers, then you are you need to slow down a little bit instead of YOLOing and just guessing, especially with these problems. But yeah, I mean, I think some variation on this I was trying to figure out, but I just couldn't. I thought maybe we just keep merging, but maybe not. Maybe I'm wrong because you don't have enough 1 bits to merge. No, that's not true, right? So what is the? I put 2. What is 2? All right. I should put it before. So I put 2 because this is 1. Oh, okay, I see. Huh. Because this is 1, which is 1 bit, but because you have 2 of them, you can make 1. You can make 1 bit, but that 1 bit is always too small. So that means that we want now to be at least k, because k is the kth binary number. It's either k or k minus 1 actually, but no, k, if it's equal to, then it's fine. And I guess as a result, this is not necessary anymore because by definition, this is not possible anymore. I think I could be wrong though. Actually, I mean that was the stricter thing. Come on, please, I want to go to sleep. Okay. All right. Well, listen, friends. Not every day could be perfect, but I probably could have been not 4 wrong answers. I mean, I tied my record, so it wasn't like I did not do better, but I also did not do worse. So yeah. And one of them was just silly because I just didn't think about it. I was just like, all right, because I wanted to focus on this. Yeah, I mean, hopefully the process made sense. I mean, it's very disjoint near the end, but I'll go over it again. The idea here is that, yeah, I mean, I think this carries most of it. If you can choose, or you're forced to choose different eyes, but if they're the same, you can choose the same, then you can merge them, right? And what I mean by merging is that, and I kind of use terminology that I didn't explain. It's just visualization. It's not like terminology. But for example, if we want to 1, 1, like if you want to, this is a binary number. If you want to get to here, and you have 5 of these operations, say, well, then you can just do 1, 2, 3, 4, and then 5 is adding just 1 more to here. I mean, I guess you'll be like, no, this is right. If you add just 1 to the thing, then this become 5, and then that you could fit it. So you can always do that in some order to kind of shorten it, right? So that was the core idea that's similar to this idea, but with the quote-unquote merging idea. Initially, I thought you could only merge 2 numbers in a row by choosing the same one. I mean, you keep doing this, so I don't know why I didn't think of it that way. And that's where you got the thing. But then the case that we failed on was that if you have 1, and you have, let's say the difference, the now is 1. Let me write it. Now is equal to 1, and k is equal to say 3. What our logic was saying is that you can do 1, 2, and then convert this to 100, so it only has only 1 bit. But you cannot do that because if you do that, then this is obviously bigger than now, so you cannot get any number. And the reason that I was I thought you can, not that I thought you can, but my code, I wrote the code such that it looked like you can, is because they both have 1 bit, and because they have 1 bit, you can construct any 1 bit, but I was wrong in that, and yeah. And so then the now is greater than you go to k is that, okay, we have k is equal to 3, so what is the smallest number that we can create, right? Well, it's just what we said, right? So it's 1, you just add 1 every time. So then if you add 1 every time, you add 1k times, so it's going to be plus k, and as a result, then it is just k, right? So that's why I have here, and then that's it. But also, honestly, some part of this is like me lying in a way, right? Like, I mean, it's easy to explain the answer when you know the answer, but going forward is the hard part, and hopefully that's what this video shows you, right? Like, I don't know, if you're still here, leave a comment about you're still here. But what I want to, why I say it that way is that if you kind of just, if you watch this video, most of it, all of it, whatever, if you kind of mentally edit it, like in a way, like other YouTubers do, such that you edit out all the parts where I'm wrong, then it'll just be like, wow, Larry's a genius because he's just able to, he's just like, oh yeah, of course K is equal to now, K is less than equal to now because how did Larry gets it so quick, etc. Right? But this is why I show everything because clearly. I have my weak points, and this is clearly one of them. But yeah, I mean, we don't have to do complexity, right? This is complexity over B, where B is the number of bits. I mean, I guess you could also say this bit square because maybe bit count is over B. I actually don't know how it's implemented, but because bit count can also be an opcode, right? And in an opcode, I guess it's all of 1, but that is only because you have a constant integer with, right? Which but so if you really want to be pedantic and nuanced, there's a lot you could go like really deep in terms of like, okay, well, if you're varying it by number of bits, then are you actually, I don't know. So I don't know, but these are things that if you talk about like in an interview, you can just talk about it and have fun with it. But for now, you can make up whatever you want. But that's it. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.